Thanks for the kind introduction. Whoa, that's loud. Usually I'm the person who gets told to keep my volume down, so I don't really need the mic too much. So thanks for coming. You guys are going to be my guinea pigs. This is my first time giving the talk. So I'll be talking about learning from dynamics. And my main focus in this talk will be on giving you new, exciting algorithms for learning linear dynamical systems. But first, what I want to do before I get there is I want to explain what a linear dynamical system is. If I can get this. OK, there we go. So let me tell you what a linear dynamical system is, and then I want to explain all of the wide-ranging applications they have, and then we'll dig into the learning problem. So a linear dynamical system is determined by these two guiding equations. So we'll take a moment to think about what these equations mean. But a linear dynamical system you should think of as being the canonical model for time series data. So the important things are that you have inputs and you have outputs. And what's going on under the hood of the linear dynamical system, but you don't see, is that there's a hidden state that's evolving. So all of these things are vectors and matrices. My inputs are the UTs that are either inputs or control. What I see are these observations, the YTs. And then we have these hidden d-dimensional vectors, these XTs, that evolve on their own under the hood. So these matrices, all have special names because they play an important role for us. The matrix A is especially important. This is called the transition matrix. It describes in the absence of input how the system would evolve. You also have the B matrix, the control matrix, that describes all of the inputs that you see to the system. What parts of the state do they touch? And then finally, we have these sensing and feed-through matrices, which just describe how our observations relate to the hidden state and the controls that we see. And last but not least, this entire process is not deterministic. We have noise elements. So we have some process noise that adds jitter to the trajectory of the underlying dynamics. We have observation noise because the YTs we get only give us some partial information about what's really going on. So these are the two defining equations, and we'll spend some time digesting them. But first, what I want to do to convince you that these things are important is I want to tell you about some of the amazing applications. Now, a lot of times when you give these kinds of talks, you talk about applications. And they're not real applications, but these are real applications. I meant to say that with gravitas. So in fact, they played a key role in the literal moon landing. The literal moon landing. Because what you want to do in a lot of these applications is you want to do some kind of tracking of an object that's moving. Now, you get very noisy measurements of where the object is. But the important thing is that you also have some knowledge about how the object is supposed to be moving. You understand the underlying physics. And that helps you much better estimate the trajectory or the flight path, like in the case of the space shuttle. In fact, linear dynamical systems not only played a key role in the moon landing, but they garnered the National Medal of Science in 2009 for their work. So the way that they work in this application, what would be my hidden state? Well, it would represent the object that I want to track. I could encode in a high-dimensional vector the position, velocity, and acceleration. And the important thing is that my transition matrix A describes the underlying physics because it tells you how the velocity affects the change in position, how the acceleration affects the change in velocity. You can also talk about in applications in biology. In fact, there are applications that are all on our minds for the past few years in epidemiology. And these are also examples of linear dynamical systems if you think about them. Right? When we think about how a virus like COVID spreads, well, we spent a lot of time trying to predict what these curves look like of how many people are infected and what the hospitalization rates are going to be. And at the end of the day, what we have is we have a system in which we categorize people into different groups, like whether they're susceptible to being infected, whether they've been exposed, whether they're infected, or whether they're recovered. And then our underlying transition matrix A just describes the transitions in some state machine of how people from one group move to other groups. In fact, the thing that I'm showing you right here is actually taken out of an actual paper modeling this in biology. And what they do is they create an even higher dimensional linear dynamical system where they stratify the population based on age group and find much better fits. So you have one separate model for each one of these underlying subpopulations. You can also talk about applications in medicine. So if you think about the way that we do drug analysis in medicine, the gold standard is a randomized control trial. So we want to figure out whether some drug is effective or not, and we take our cohort of patients and we randomly split them into the trial and the control group. And then we try out, medicine on one and a placebo on the other. But the truth is that in a lot of modern applications in medicine, we want to try out drugs in terms of their effect in a very personalized sense. We can't always create a very large cohort of patients that are close enough to each other. So one of the strategies, which is very popular in medicine these days, is what's called an N of 1 trial, where you try to do a randomized control trial, but with a single patient. That sounds too good to be true, but the idea is that you take this one patient and you randomly switch which of the medications you're giving them, and you measure the response of the patient over time. And what you're hoping to do is to infer from observing that trajectory of dynamics how effective the medicines are. So you really want to do learning and inference with a linear dynamical system. In fact, this is by no means a comprehensive set of applications. There are all kinds of applications in things like speech processing, econometrics, finance, and so on and so forth. But really, just to take a step back, when we understand these two governing equations for linear dynamical systems, what makes them so widely used? It's really the fact that we can do a lot with them. So if you told me all of the parameters of this model, if you told me the A, B, C, and D matrices, you told me the distributions of the process and observation noise, well, when the model's fixed, I could talk about doing things like inference, right? That's what happens with the space shuttle, is I know the underlying model, and I'm given noisy observations, and I'd like to compute the posterior distribution on what the hidden state is, so that I can estimate the trajectory. So the great news is that linear dynamical systems are models which are very tractable in this regard. There are polytime statistically optimal algorithms for performing optimal Bayesian inference in them. So once we have the models, we can do a lot with them. But there's one question which is on my mind, which is, how do you get these parameters? So there's some settings, like in the physics application, where they would come from discretizing some ordinary differential equation. But there are other applications, especially in data science, like you think about the epidemiological application, where you'd like to learn them from data. So what can we do about learning the parameters of a linear dynamical system? This is a topic that's been studied for 50 years in control theory. Usually it goes under the name of system identification. But shockingly, there are extremely wide open questions even for this very basic question. So what I want to do right now is I want to formalize what the main problem is. We'll work through this slowly before we get to the precise statement of what I want to do. But I'm going to set the strongest possible learning goal, is that I want to learn a linear dynamical system not from many trajectories, but from one single very long trajectory. It's not even obvious you should be able to do such a thing. So what I'm going to get is I'm going to get a very long sequence of inputs, and I'll get a very long sequence of the outputs. And there's a lot of information stored here because I know, how inputs over time affected the output downstream. Maybe they don't even affect it instantaneously, but they affect it after 2 or 3 or t time steps. But what I'd like to do is take this one long trajectory, and I'd like to determine accurate estimates, A hat, B hat, C hat, and D hat, for the linear dynamical system. In fact, I'm going to set an even stronger goal than you might think. I want these new parameters I've estimated, A hat, B hat, C hat, and D hat, to determine a linear dynamical system that is equivalent to my original one. So what do I mean by a linear dynamical system being equivalent? Let's take a brief aside before I introduce the quantitative way that I'll measure parameter distance. Well, one very strong notion of what it means for two LDSs to be equivalent is for them to have the same input-output functionality. So if you tell me some strategy of, if this was the sequence of inputs and outputs I've observed up to time t, I have some arbitrary function that tells me what my next input is going to be. Well, that's going to result in some distribution on the trajectories. I want the property that the true LDS and my learned LDS have exactly the same input-output functionality, even for adaptively chosen inputs. Now, the thing which I'm just going to assert, which will get us closer to formalizing the question which I'm really after, is I'm just going to assert the following, which is true, is that two linear dynamical systems turn out to be equivalent in this sense that I wrote down here, if you can relate their parameters by an appropriate change of basis. So if there's an invertible transformation U that relates A and A hat in this way, relates B and B hat in this way, and so on. So what I claim is that this now defines a very natural notion of a parameter distance for our purposes. How well do I want to learn A, B, C, and D? I want to learn them well in the associated metric that follows from this proposition. So in particular, the way that I'm going to formalize the question is we're given one long trajectory, and we'd like to estimate A hat, B hat, and C hat, and D hat such that there is some unknown invertible transformation U, so that after that transformation, all of my parameters are close to the truth within an additive epsilon in Frobenius norm. So this is my main question for this talk. So in fact, one thing that's really not obvious is whether there's a polynomial time algorithm. In fact, it's not even obvious whether the problem is possible information theoretically. What makes this problem tractable in the first place? So there's no exaggeration to say that there are hundreds of papers on this topic, maybe even thousands. It's a bit hard to run down the laundry list of all of the assumptions that people have tried out. Some of them are pretty exotic and strange. They're things like norm bounds on the coefficients of the characteristic polynomial of A, properties about its behavior in the complex plane. But one assumption that underlies essentially all of the earlier work is something that sounds like a pretty benign assumption, but I want to make the point that it's really a pretty damning one. So what I'll focus on is one particular assumption, which has to do with the spectral radius of the matrix A. So the spectral radius, remember, is the largest absolute value of any eigenvalue. So if you assume that the spectral radius is strictly less than 1, that's called strict stability. If you assume that it's less than or equal to 1, that's called marginal stability. And that might look like a slight change. I'm changing a strict to a non-strict inequality. But what I want to convince you of on this slide is that it's a very fundamental difference, right? So what does it mean when something is strictly stable? First, I claim that it fails in really simple cases we care about. In fact, I've already told you about some of those examples. If we think back to the moon landing example, the transition matrix had to do with the laws of physics. So how exactly does velocity change position? How exactly does acceleration change velocity? The underlying transition matrix would be an upper triangular matrix with ones along the diagonal, and it would absolutely not have eigenvalues that are strictly less than 1. So the truth is that usually when you discretize an ODE and you create a discrete approximation to it, what you get is absolutely not strictly stable. And that's really because of something pretty fundamental, which is that what strict stability means is that there are no long-range correlations. So what if I told you the hidden state xt, and then I asked you what effect this has at the hidden state at some much later time? Well, when the spectral radius is strictly less than 1, everything is exponentially contracting. So that means that xt doesn't have any effect, virtually, on what happens much later on. In fact, what this really means is that even though you're trying to learn from a single trajectory, when there are no long-range dependencies, in effect, the things become independent if you wait long enough. So marginal stability doesn't have any of these conditions. That's what makes it so tricky. If you don't have marginal stability, the problem really doesn't make sense in the first place, because it means you have an explosive system. So it's just growing in norm exponentially, and then the fact that the noise is some fixed additive amount doesn't even make sense to begin with. So what I'm really going to focus on is, what we can do with marginal stability. Yeah? They're going to be stochastic. So we are not even allowed to choose them. In principle, you could be allowed to. We won't need any of that. So the problem is that, if you could choose them, it's very hard to make it a well-posed problem because I could just make it so gigantic that nothing in the past really matters. And then it kind of trivializes the problem. So in a lot of applications, it makes sense to talk about exerting some kind of control on your system. That's why it's called a control. But the truth is that usually you're limited by not exerting a very large magnitude control. So for our purposes, because we don't even need to control them and almost any distribution will suffice for us, I think it's actually better to think about it as a disturbance rather than a control. So even if you have some exogenous driving thing that jitters your system, as long as you can observe it and the correlation between that and your output, that's enough to learn. But great question. All right, so in fact, algorithms that work based on strict stability, the thing is that quantitatively, they have a dependence that looks like 1 over 1 minus the spectral radius. So they degrade and blow up as the spectral radius goes to 1. And so the conceptual question I want to ask is, do long-range correlations obstruct learning? Now, the truth is, I'm an algorithms person, so if I'm asking this question, obviously the answer is no. But we'll see that there's some surprises along the way. All right, so the next thing that I want to tell you about is that, I told you there's a wild west of assumptions in these hundreds of papers, thousands of papers on learning linear dynamical systems. Well, I claim that there is a notion of what are the right conditions that make the problem well posed. You do need some kind of assumptions on the linear dynamical system, but I'm going to tell you about 2 conditions that are necessary and sufficient, in a sense. So the first one is what's called the observability matrix. So what you do is you create a block matrix, which the first matrix in this block is C, and then you stack it on top of CA and CA squared and so on. But the important thing is to have a good way to interpret what this matrix means, right? Because what I claim, and we'll walk through this, and this will give us a way to interpret what's going on. I claim that if this matrix doesn't have full column rank, you're dead. It's not even information theoretically possible to learn the linear dynamical system. So let's do some elementary linear algebra. So what does it mean for this matrix to not have full column rank? It means there's a non-zero vector that lives in its kernel. So what that non-zero vector gives me is it gives me a way to change the underlying state so that I don't observe that change immediately, because the C matrix describes how that change affects my immediate observations. Not only do I not observe that change immediately, I don't observe it at the next step, because when I apply the matrix A, that allows the system to progress by 1 step, and then I still don't see it. And then I still don't see it even after S time steps. So this observability matrix captures what parts you can see of the system linear algebraically concatenated over S consecutive time steps. And when it doesn't have full column rank, that means that there's some portion of your state space that you're blind to. And the same way we can talk about the observability matrix, which is also a block matrix. We concatenate a bunch of matrices together. It's B, AB, and so on, A squared B. And if this matrix doesn't have full row rank, you're also in trouble. So why are you in trouble? What does it mean to not have full row rank? It means you can left multiply by a non-zero vector to get something 0. And what that means is that there's some direction of your state space that you can't touch with your control. You can't immediately move in that direction instantaneously. You can't move after 1 step. You can't move after S steps. So there's some part of your state space that's inaccessible. So all of these propositions really go back to the first work in control theory due to Kalman in 1960, where he showed that these assumptions are necessary in an asymptotic sense, that if you literally are degenerate for either of these matrices, then the problem is impossible because there's a smaller linear dynamical system with smaller order that still fits the same data. We'll need quantified versions of this, but what I claim is that these are the right conditions that make the problem tractable. So let me tell you about our main results. So what we showed in joint work with Ainesh Bakshi, Alan Liu, and Morris Yao. So we gave a polytime algorithm for learning a linear dynamical system, as I promised, a marginally stable linear dynamical system from 1 long trajectory. And it has polynomial running time and sample complexity guarantees. And it only depends, the only assumption we need is that you need that the observability and controllability matrices are well conditioned. So you need some quantified version of the fact that they don't have, that they're not degenerate in terms of rank. But moreover, what you can show is that these conditions are necessary, information theoretically, that if you do not have bounded condition number, that the problem is impossible, information theoretically. All right, so I want to say a few comments. So first, there is one earlier work by Simchowitz et al. Where they gave an algorithm that works under marginal stability. But there's a pretty big caveat, which is that it depends, it has hidden constants that depend arbitrarily on the underlying linear dynamical system. So nothing in the world prevents those hidden constants from being exponential in the size of the linear dynamical system. So these aren't really what I would call polytime algorithms because they're not polynomial in the number of parameters you're trying to learn. I want to make one more qualitative point, which I'll just make as an offhand motivation. So you could wonder, there was all this work in control theory in the 60s on the problem of system identification. And all of a sudden, in the early 2010s, there was a huge flurry of work on learning linear dynamical systems. So one of the reasons why people all of a sudden returned to it was they wanted to use it as a metaphor for much more complicated systems. There are things called recurrent neural networks that are basically very, very deep neural networks that act like a time series. And we'd love to understand whether gradient descent works on fitting the parameters of a recurrent neural net. That's a very nasty problem to solve because it's insanely non-convex. But what people do instead is they try and understand whether you can learn linear dynamical systems as a metaphor for trying to understand what's going on with RNNs. But the point I want to make is that even the information theoretic foundations of learning in LDS weren't understood. And maybe before we jump to trying to analyze gradient descent to understand RNNs, we better understand the fundamental limits of learning LDSs, especially if we're using them as a basis for reasoning about much more complex systems. And in particular, we better understand which of these bevy of assumptions really are necessary or not. All right, so that was a long introduction. Now I got to metaphorically roll up my sleeves, and we should talk about some of the technical ideas. The algorithm is actually based on some very simple ideas, which is good, is that I'm going to try something very simple. In some corners of learning theory, there's an approach that's very effective, which is called the method of moments. It has wide-ranging applications. It's something that was introduced over 100 years ago by one of the founders of statistics, Carl Pearson. And it works very simply. You want to solve some learning problem. Like I want to learn the parameters of some underlying distribution, given samples from it. And I just follow this simple blueprint. So the first thing that I do is I use my samples to estimate the moments of the distribution. And then once I have estimates for the moments of the distribution, I set up a system of equations that constrains what the moments tell me about the underlying parameters that I want to estimate. And then I solve those equations. This simple blueprint has tons of applications, especially in modern times, when you can actually do these things algorithmically with the right kinds of tools from tensor methods. But basically, the method of moments is the driving force behind a ton of work in unsupervised learning. You can use it as a basis of learning hidden Markov models, learning mixtures of Gaussians, learning topic models, solving robust estimation. And what I want to ask now is, maybe instead of doing gradient descent to try and learn a linear dynamical system, can I use the method of moments? So is there some way to take this blueprint that goes back to Carl Pearson and port it to time series analysis, but critically, to get it to work in cases where the data is not stationary? So let me tell you about the blueprint we're going to follow, which is that we're going to learn what's called the Markov parameters. Those are the natural analogs of moments of a linear dynamical system. That first thing, I don't know what happened there. That should be the D. But Markov parameters are just a concatenation of a bunch of the matrices that define an LDS. You can ignore D for simplicity. But you should think of the Markov parameters as really governing the input-output functionality of the system. So we're going to follow a two-step procedure. First, what I'm going to do is I'm going to take my trajectory and use it to estimate the Markov parameters. And then I'm going to show that the Markov parameters allow me to determine A hat, B hat, C hat, and D hat accurately. So that's our blueprint. In fact, the second step of this blueprint is really a pretty widely known thing. OK. All right. All right, let's just see what happens here. Hidden under this black box is not anything mysterious, but I'll have to explain it in words, sorry. So the second step in this procedure is something that's very well known. It's called the Ho-Kalman algorithm. So what I'm going to do is I'm going to take the Markov parameters that someone gave me, and I'm going to form a Hankel matrix. Let me write it down because it's blacked out here. But the way that the Hankel matrix is going to work is that in the top left corner, we're going to have CB. Then we're going to have CAB along the first anti-diagonal. And then we'll have CA squared B, and so on, all the way along this anti-diagonal. And I'm going to cut up this matrix. So I cut out the last column, and I'm going to call that matrix H1. And I cut out the first column, and I'm going to call that matrix H2. So nothing very fancy is going on here. What I'm doing is I'm taking the Markov parameters that someone has given me in the second step, and I'm rearranging them into a structured matrix. Now, the crucial thing that you can see from the structure of this matrix is that it actually is related to something that we want to find. So if you remember the observability matrix, what does it look like? It's C, CA, CA squared, and so on. What's the controllability matrix? It's B, and then AB, and A squared B. So when I take the product of those two matrices, O and Q, I get exactly this Henkel structure. That's the crucial thing. So the important thing is that I know the left-hand side because someone gave me the Markov parameters. And these O and Q matrices that I wish I had are a hidden factorization that I'd like to find. So now the way that the Ho-Kalman algorithm works is it's really just a very simple procedure. What I'm going to do is I'm going to find any other decomposition of this matrix. And then I'm going to argue that that decomposition must be equivalent to the hidden one that I started from, which I wish I had. So the crucial thing is that I'm going to take this matrix H1, which remember is all but the last column of my Henkel matrix, and I'm just going to form another decomposition by taking its SVD. And then I group terms in the SVD, so I combine U sigma to the 1/2, and I combine sigma to the 1/2 in V transpose. And I'm just going to call the first part O hat and the second part Q hat. And I'm going to hope that O hat is related to O, and that Q hat is related to Q, the observability and controllability matrices. In fact, we already know that there is a hidden factorization of H1 that's related to the true parameters. So on the one hand, I have two factorizations of the same thing. Now what I claim, and this is really just elementary linear algebra, is that since O and Q and O hat and Q hat are two equivalent factorizations, provided they have the right non-degeneracy conditions, namely they have full column and row rank respectively, then it must be the case that there's some invertible transformation that transforms one into the other. Otherwise, you could not possibly have the right row and column space to both get the matrix H1. So now we're in good shape because we found, using what we know from the Markov parameters, we found some other decomposition that we can relate to the one we want by some change of basis. And the last thing we should do is figure out how to estimate the rest of the system, namely A. So how can I find my estimate A hat? So the crucial thing here is now I'm going to use the second part of this Henkel matrix, where I threw out just the first column. That also has a description in terms of the product of O times Q. But notice that all of the terms that show up in H2 have at least one power of A. So I can actually write it as an observability matrix times A times Q. So now I'm in good shape because I can just, using from step 2 the fact that O is related to O hat by a linear transformation, the fact that Q is related to Q hat by a linear transformation, well, I can rewrite this expression. And now all I have to do to find a good estimate of A is I just left and right multiply by the appropriate pseudo-inverses, and I'll get exactly my estimate A hat, which is equal to A up to some change of basis. So that's the Ho-Kalman algorithm. This goes back to the 1960s. This was my exposition of it because I had a hard time reading the original paper. But this solves step 2. This is something that was known in the 60s. Sort of. So really, if you think about this two-step blueprint, right? In the first step, I'm only estimating the Markov parameters, so no one's going to give me them exactly. At best, I'm going to have very accurate estimates for those parameters. So what I should really care about is in the second step, how stable is the algorithm? What happens if I perturb the Markov parameters and I only get very accurate estimates? Do I have a guarantee that the output of Ho-Kalman is also close to the true parameters? This can be done. This was done in a paper of Oymak and Oze. I'm not going to state the bound. I'm not going to show you the proof. But you should think of this as being something that you could do because it follows from the stability analysis of the SVD itself and carrying through how the errors compound over the steps of the algorithm. So now we get to closer to the heart of the issue, right? What really happens inside any paper for learning linear dynamical systems is you've got to solve step 1. How do you learn the underlying Markov parameters? That's where the action is, and that's where we're going to do something pretty new and radically different. But before I do something new, let me do something trivial. So in fact, what I'm going to do is I'm going to take, what I want to do is I want to estimate the Markov parameters, and what I claim is that there's a trivial estimator that's an unbiased estimator for the underlying Markov parameters. When I tell you this, it's going to sound like we should just be done. Step 1 should be solved. I promise you we won't be, but let's just go with this. So first, what I claim is that where the Markov parameters come from is they're just the covariance between the inputs and the outputs, where you vary the time lag in between them. Now, once I tell you this observation, I mean, shockingly, I didn't see this observation in the literature anywhere, even though it's trivial and important, but there can only be one proof. You just check it. So what can I do? I just unravel the recurrence. Let me try it out for j equals 1 when I'm looking at the covariance between yt plus 1 and ut. And I can take my defining equation for a linear dynamical system. And now I want to figure out where the UTs are in this expression, so I unravel the xt plus 1 and use the second defining equation. And I get this mess of an expression with 5 terms. But thankfully, the covariance against UT is 0 for all but one of them. The only thing that has a non-zero contribution is the part where UT shows up. And if I've assumed that the covariance of the noise is the identity, I pick out exactly the CB matrix, the first non-trivial Markov parameter, as my expectation. So that's it. So now you should be wondering why I'm not done, right? Because there were 2 steps. Get the Markov parameters and use them. And we have an unbiased estimator for the Markov parameters. So there's something very natural you can try, which is even though you only have one long trajectory, well, you can vary little t and get different estimates of the underlying Markov parameters. I can just time average over different t's, but keeping this j fixed of the time lag. These will all be unbiased estimators of the underlying Markov parameter, but this approach completely fails. It fails because of dependence. So if these estimators were unbiased and were independent of each other, then the variance would be going down as capital T increases, but not if they depend on each other. In fact, you could take a trivial time series, one which is just a Gaussian random walk. That's not even converging. There's no hope that this estimator has bounded variance because it's actually going to infinity as capital T increases. That's terrible. So just as an aside, I belabored this point that strict stability trivializes the problem. Now it's easy to see why. When it's strictly stable, remember that if we wait long enough, we get independent samples. So then I can just take independent samples from my long trajectory just by taking one observation, getting an unbiased estimator, waiting a long time for mixing, taking another one, is that, assuming mixing trivializes the problem, and that's really getting around it is where the action happens. So in the last, 15, 20 minutes of the talk, I can finally tell you what's new. So let me tell you about a new idea for how to salvage the method of moments, which is what we're going to do is we're going to engineer a better time series. We're going to take our old time series, the YTs, and I'm going to form a new time series that's going to come from a linear transformation of my old one. So is there a way to choose some CJs so that my new Y hat results in a good estimator? So what do I want, just to be precise, out of this estimator? First, I want the property that it keeps the expectation unchanged, because I want my new time series to still be the basis for giving me unbiased estimators for the Markov parameters. But then I want these CJs to do something good in terms of stabilizing and controlling the variance. So is there a good choice of the CJs, which has the property that the new estimator, even though it has the right expectation, now has variance which is bounded independently of little t. So that's our roadmap for how we're going to fix this approach. And it's very hard to understand what the strategy is in one go, so I'm just going to work up towards it with a bunch of thought experiments. Let's try a clever choice for what to do with the CJs. We can take the characteristic polynomial of the matrix A and look at the CJs as the coefficients of that characteristic polynomial. And I claim that this will be a very good first start. It's definitely not going to work, but it'll get us going. So why does the characteristic polynomial make sense as a starting point? First, we can recall the Cayley-Hamilton theorem. That tells us we take the characteristic polynomial for a matrix, and we replace the formal variable x in that polynomial with the underlying matrix A. And the statement of the Cayley-Hamilton theorem is that when you apply the polynomial to the matrix A, you get the all-zero matrix. In particular, for us, it tells us that you can write a high power of A as a linear combination of the lower order powers of A. So this is our building block. And what I claim is that the Cayley-Hamilton theorem is going to create exactly the right cancellations where all but the transient terms get canceled out. So, you can prove this just by writing down a mess of equations. And I couldn't even fit the equations on the board, but they're also not very instructive. And maybe if I put them in my slide, they would be blacked out with a graphics glitch too. But let me convince you that it ought to be true. Let's think about a special case where we make our problem much simpler. I'm going to set the D matrix to 0. I'm going to get rid of all noise. But this is still where the action is happening. So I just have these two defining equations for the time series. And I can write out y hat t plus 1 in terms of the other y's. Right? So this is the general strategy I have, and the CJs come from the characteristic polynomial. Then I can use the fact that y is related to x to write down what each of those expressions are. And then I can organize terms in a way where I want to collect the different UTs. And so I can take each term and expand it based on its recurrence, and I'll get a UT and an XT term at a smaller value of t. I can take the next expression and expand it so that I get new XTs and UTs from the previous time step, and so on. And the thing that you notice is that if you look at the UT portion, the first row, there's no way to cancel that term. There's only one UT. But if you look eventually down this matrix, right, every row, at some point, you're looking at higher powers of A combined with lower powers of A, and the way that you're subtracting them off is exactly the right way. That comes from the Cayley-Hamilton theorem. So the key point is that in this expression, you eventually get cancellation, and things don't survive for that long. So the important thing is that if you work this out, what you get is an expression in which you group together the transient terms that don't have, that have a small number of components to them, and you have some much bigger expression that has to do with the much further back UTs, and all of the latter go away. So you're left with some expression which now has variance which is bounded independently of t because there's only n squared terms. So it's something extremely natural to try this strategy. So the variance is bounded independently of t. That's great. We engineered a better time series using the Cayley-Hamilton theorem. But unfortunately, we messed up the first goal. I want the expectation to be the Markov parameters. And if we take the expression we had on the previous slide and we look at it, what I care about is the covariance between y hat t and some ut minus I, some earlier control. But you can see that I have not only the expression. All right, so we can see again. All right, so the last point that I was trying to make was that we're trying to make sure that the expectation is preserved, right? But what I care about is the covariance between y hat t and a ut minus I. That's how it's supposed to work. But you can see the term I'm supposed to pick up is this first term right here, because that's the Markov parameter. But I've created this whole mess of other terms that mess up my estimator. So let's fix it. It turns out there's a pretty simple way to fix it. So the second attempt for how to fix it is that all you have to do is you use time lag. So who says you should cancel t using t minus 1, t minus 2, and so on? Maybe just wait a little bit, right? So here I'm trying to cancel yt, but using only things that are yt minus r and further back. And so the crucial thing about this is that if you look at this expression, then if you expand it out using the same tricks I gave you before, there's none of those other UTs are going to show up there, so I don't actually contaminate the expectation. So that's great because it means that we've now solved the other problem. So we have something where we've controlled the variance and it's independent of t, and also by using this time lag trick, we've actually made it be the case that we still have an unbiased estimator of our Markov parameters. And so we still cancel out these long-range dependencies, but let me tell you about the third attempt. Now, it's not obvious why I need a third attempt, right? Because I only had two problems, and it seems like I fixed them. There's a problem which maybe you didn't see coming, which is that I lied. So, the issue is that the coefficients of the characteristic polynomial, they could be exponentially large themselves. There are very simple linear dynamical systems in which the characteristic polynomial would be extremely large. So it turns out that there is a trick for how to solve this too. I'll briefly just mention it before I transition towards the end, which is the key is to appeal to these notions of observability and controllability. It turns out that what you can do is you can show that there are good CJs that exist, but it's only true if you actually use more than just the bare minimum number of powers of a. I'm trying to write a to the n as some linear combination of the lower order terms, but no one says I can't use more than the smallest number. So once you use more than that, when the problem becomes well conditioned, that's exactly when you can show bounds on the size of the coefficients that you need. And so at the end of the day, what this means is it tells us, once we solve all of these problems, it tells us that if we knew the observability and controllability matrices, which is the thing we're after, that it would imply the existence of good CJs that corrects our method of moments estimator so that we can execute step one. So that means we create an unbiased estimator that has controlled variance independent of the fact that the time series is growing and changing in complicated ways. And at first glance, you might think that all of this sounds circular, because the thing that I want to do at the end of the day is to find the observability and controllability matrices. So it turns out, and the last thing that I'll mention is that you can use convex programming to the rescue. So what you can do is you can write down a convex program to search for the CJs now that you know they exist. So what do? I look for CJs that are bounded because of observability and controllability, that have the property that they control the empirical fluctuations of my new engineered time series. Now, even here, analyzing this convex program is, pretty involved, because, what I'm constraining, and the second constraint is the fact that my new y hat t doesn't blow up, right? But, no one's to say that the CJs I find, if I reran the linear dynamical system, it wouldn't cause a blow up then. Maybe the CJs I found were just an accident. So the way that the analysis goes is that you define some appropriate potential function that captures the potential variance as if you were to rerun the time series from scratch. And you show through the right kinds of anti-concentration that the only way that the potential variance is large is if with high probability you would have actually violated one of these constraints and you would have actually been large for some y hat t. So that's how the overall algorithm works, is that you can basically stabilize the moments. You can write down a convex program to combat the fact that the time series has very strong dependencies, because the same tools you use to stabilize a linear dynamical system, you can use to get better estimates of the underlying dynamics. So I'll briefly mention that what's kind of fun is that you can ask for this strategy to go even further. So what I'm very excited about is that if you think about it, in some corners of learning theory, the method of moments is extremely powerful and we understand how to use it. But maybe the method of moments could be used in these other corners, like time series, where there's non-stationary data. Even better, maybe there's a dictionary in going from how to use tools that we already know and love in one corner to how exactly they should work in these more exotic areas. So you can ask all kinds of fancier things, like what happens if you have a mixture of linear dynamical systems? This is what the method of moments is really useful for. Some of the other work that we gave, exactly gives some kind of generalizations of this to learning mixtures of linear dynamical systems under, again, essentially minimal conditions, something to do with joint non-degeneracy. So I'll stop there, and I'll mention what I hope you got as the main takeaways. So in the beginning of the talk, I introduced what linear dynamical systems were through their defining equations. They have tons and tons of applications to the world around you. But the problem of trying to learn the parameters of an LDS is a very complicated thing. Now, it turns out that you can get a very simple blueprint to work where you write down a method of moments estimator to learn the Markov parameters and then use the Ho-Kalman algorithm. But there turn out to be some surprising twists to how exactly to use the method of moments, because you have to figure out how to stabilize those estimators through convex programming. And at the end of the day, we got an algorithm for learning linear dynamical systems that succeeds with essentially minimal assumptions that are all information theoretically necessary. So the question I'm pretty excited about these days is really about learning under dynamics more generally, not just here in control theory, but in reinforcement learning. And what I wonder is all of these tools that we know and love in unsupervised learning, is there some methodological way of porting them to new domains to get exciting new algorithms and hopefully answer Jesse's question down the line? All right, so thanks.